Hello, grade sevens. I hope that you are all doing well and that you are ready to get started in the next unit of study in Math 7, where we're going to look at different ways of adding and subtracting integers. Before I jump into my PowerPoint notes, I did just want to quickly identify what the primary learning outcome is from the grade 7 Alberta Program of Studies. This learning outcome falls into the number category or STEM. The N6 just means it's the sixth learning outcome in that category. And the learning outcome is going to be to demonstrate an understanding of addition and subtraction of integers concretely, pictorially, and symbolically. So as we go through the unit, there's going to be a couple different ways that we do the addition and subtraction of integers. One way is going to involve using integer chips, and the other way is going to involve using number lines. And then hopefully by the end, after we've used the integer chips and number lines enough, we'll be at the point where we don't really need to use them anymore to add or subtract integers. Okay, so let's get into this. So the very first thing that I want to do is just provide a definition of what an integer actually is. And an integer is any positive or negative number that must be whole and the number 0. So what I'm going to do right here is I'm going to write down a bunch of numbers. And as I write these numbers down here, I just want you to think about whether or not these numbers would fall into that definition for an integer, whether the number is a positive or negative whole number or 0. Okay, so here's a few numbers. I'm going to write down -4. I'm going to write down 2.5. I'm going to write down 0. 25/5. 6.0 and 7/2. Okay, so 6 numbers, and I just want to identify if these fall into the category of being an integer. So the first one, -4, that is an integer. It's a negative number and it's a whole number, so that one is good. Second one, 2.5. Well, that's a positive number, but it's not a whole number because it has that half portion to it. So 2.5 would not fall into the category of an integer. So I put an X there. 0, well, the definition flat out states that 0 is an integer. So put a check mark here. Now, fraction might be a little bit confusing to look at. What I would do is, to determine whether a fraction is an integer or not, I would take the numerator and divide by the denominator and see if it divides evenly. So 25 divided by 5 would just be equal to 5. So it does divide evenly and it gives you a whole number. So 25/5 would be an integer. 6.0, that's a positive number, although it does have a decimal, but the decimal doesn't mean anything. The 0 right here doesn't really add anything to the number 6. In fact, there's no reason why you couldn't just write this down as 6 here. So since it's a positive number and it's whole, it is an integer. And the final one I have here is 7/2. So again, if you have a fraction and you want to know if it's an integer or not, I would just go top divided by bottom. So in this case right here, 7 divided by 2 would give you 3.5. So you've got that 0.5 portion of the actual number, again, a half of a number. So we need to have whole numbers. So this is not going to fall into the category of being an integer. Okay, so of those numbers I wrote down, 4 of those 6 numbers did fall into the category of being an actual integer. Now, the way that we're going to represent integers is by using something called integer chips. Just to explain how we actually model the integer chips, they're kind of like bingo chips. They're just like circular chips of a specific color, and different colors are going to tell you whether the chip is positive or negative. So our positive integers we can represent with red chips. For example, if I wanted to visually model positive 4 being an integer, I could model it with 4 red chips. So the plus right here just indicates that I'm going to use red to represent all the different whole integers. Negative integers we are going to represent with blue. For example, visually modeling -2, well, the negative is going to tell you that you're going to model the integer with the color blue, and the 2 tells you how many chips to actually draw. So in this case right here, you'd have 2 blue chips. I suppose if you wanted a way to like memorize this, again, I'm just staying consistent with the way that like the textbook we use actually color codes these integers. If you think of like a thermometer, I could associate like really, really cold temperatures, like cold temperatures being in like the -°C, maybe with the color blue. And I could associate the color red as something that's really, really hot. And really hot temperatures would have, you might associate with the color that is red. Like think of like lava or something like that. So third example, we're now going to do integer addition using the actual chips method. I have 2 parts here. Part A, we're going to take +3 plus -3 and figure out what that's equal to. In part B, we're going to take -4 and add +2 and figure out what that's equal to. Now, I just want to point out one thing right here. You'll notice when I write down the actual integers, like the proper notation to write them in is in brackets. The easiest way to explain this would be like what would the statement look like if I remove the brackets? So if I remove the brackets on, for example, part A right here, this would be like +3 plus -3. It looks really weird. You have like +3 plus -3. It's difficult to tell the difference between like what the operator is and what the actual integer that I want to add together. So anytime we write down these integers, we're just going to put them inside of brackets. And then the sign that's not in the brackets is going to be the operator, which in this case right here is going to be addition. Whoops. All right. So first things first, let's just write down the two the 2 numbers that do represent the integers here. So we'll start off with part A. So part A, we want to take +3 and we want to add -3. Okay, so +3, the positive means we're going to deal with red chips. So +3 to be represented by 3 red chips. -3, the negative means blue chips. So we'd have 3 blue chips. Now, the way you add the integers together is pretend like these different colors are like perhaps like opposing armies that are about to come into battle. And the way it works is that when they go into battle, exactly 1 red chip will cancel off exactly 1 blue chip. So it's a 1-to-1 ratio in terms of what's going to actually cancel off. So in this case right here, every red chip is going to be canceled off by a blue chip. What does that leave you with? Well, nothing. You have no chips left at the end of the day. Now, this statement at the very top right here, where it says like +3 plus -3, this one right here is called an addition statement. So I'm just going to complete the addition statement now and identify what's +3 plus -3 equal to. So +3 plus -3 would just be equal to 0. So that's what the answer to part A is. Now B, I have -4 plus +2. So -4 in front of the negative in front of the 4 means blue. So -4 would be 4 blue chips. The positive in front of the 2 means red chips. So we'd have 2 red chips. So this blue army and this red army, they now come into battle. one red cancels off one blue. So we can put a little slash or a line through it just to kind of indicate that they're canceling each other off. Now, what I'm looking for right here is what's left over. So what's left over right here? Well, if I carry the number of chips that's left over down, I have 2 blue chips that remain. Now, I then go backwards and identify, well, what does 2 blue chips represent? 2 blue chips, the blue means negative, and I have 2 of them, so that'd be -2. Writing down the addition statement would give you -4 plus +2 is equal to -2, and that's a solution to that problem. A few notes about this. So if we go back to example 3, part A, we had +3 plus -3 is equal to 0. Those two integers, the +3 and the -3, we call them opposite integers. The reason they're opposite integers is because they have the same numerical value in terms of the 3, but they have an opposite sign. So I can see that. Second note is anytime you have opposite integers and you add them together, they're always going to be equal to 0. So a different way of classifying opposite integers is we can call opposite integers a 0 pair. They're called a 0 pair because a pair just means 2 things. So you have 2 integers that are being added together. But since they have the opposite signs, they're always going to cancel each other off. They're always equal to 0, and therefore you have a 0 pair. Now, this problem is going to work a little bit backwards in comparison to example 3. So it says, here's a picture of a bunch of chips. And what I want to do is I want to write down that addition statement. The addition statement is integer 1 plus integer 2 is equal to whatever the answer actually is. So in this case right here, I have 8 red chips. So 8 red chips, red is positive, would be represented by +8. 3 blue chips, the blue means negative. So you'd have -3 representing 3 blue chips. Now, let's bring these guys into battle. And when I do this, I would have 3 of these pairs cancel off. Now, if I carry down what's left over, I would have 5 red chips that are left over. The 5 red chips that are left over, if I turn it into an integer, the red means positive, so this would be +5. Now, to put this together in an addition statement, it would simply just be +8 plus -3 is equal to +5. And that's the addition statement. Now, in terms of work to complete, in the MathLink 7 textbook, we have pages 313 and 314, numbers 5 through 9. I believe 5 and 6 show you a picture and want you to write the addition statement. And then 7 and 8 want you to do the addition by showing all the work for the chips method. And then number 9 gives you a couple of word problems where you can do the same thing. You can use the chips to actually add the integers together. Or at this point, if you're feeling comfortable enough where you actually think you can carry out the addition, I would say for number 9, you can just do it. You can just write down what the addition statement is actually equal to without showing the chips. But for numbers, let's just expand this right here. So for numbers 7 and 8, I do want you to show work using the chips. Number 9, if you read the problem and you can write an addition statement down and you simply know how to evaluate it, then just do it. So for example, if like you read the problem and the addition statement was something like, let's say +6 plus -4, without even using the chips, some of you may be able to recognize that positive 6 plus negative 4 is just equal to positive 2. So that would be sufficient for work for number 9 if you do want to skip the work for actually showing the chips. But as you can see in the learning outcome at the start of the actual lesson, you are expected to represent integers pictorially. So one method of pictorially doing it is with the chips. All right. Hopefully explained how to do integer addition using the chips, and I'll talk to you next time.